What's up, everybody? Today we are going to look at Lassalle's invariant set theorem. Okay, this is the scientist who came up with that idea, right? Okay, the idea is this: whenever you have that type of system, okay, and you know that it's stable, most of the time you get that type of annoying situation where you just write the typical, I guess I can make that happen. Yeah, that type of typical Lyapunov function, quadratic function, right? And then whenever you have that, right, v dot term, whenever you explicitly express that, and you look at it, right, and you see, hey, I cannot write that in this type of form. It doesn't look obviously negative definite to me. You say that, right? And for these type of cases, right, Lassalle's invariance set theorem, this is my opinion, of course, right, is perfect, right? You just write that your typical Lyapunov function, right, and then compute and explicitly write down the v dot term, right, and then after that point you will do some type of manipulations, and then you will conclude, hey, by using Lassalle's invariant set theorem, this system is, or the given x equals x eq, right, is asymptotically stable, right, by Lassalle's invariant set theorem. Okay, all right, this is the general idea, right? This is the general idea, and now we are going to look at that. Maybe it would be better for me to just delete that. Just delete that. Okay, so, and this is Wikipedia definition of Lassalle's invariant set theorem. There is two versions of it, one global version and one local version, right? But yeah, you can kind of guess the similarities and differences. Okay, let's try to understand. By the way, it looks like a really mathematician wrote down that text. So let's try to dissect that, right? Bisect. Okay, got it. All right, suppose a system is represented as, okay, this is the dynamical system, okay, where x is the vector of variables, okay, and this is our equilibrium point, okay, x equals 0 without loss of generality, okay, if, and that's like to state f being, or not f being, v, Lyapunov function being smooth, okay, all right, that means a smooth function, okay, set of smooth functions, all right, can be found such that, okay, all right, first of all, what would that imply when we have this and this? It would imply just stability, or stability in the sense of Lyapunov, right? However, let's look at this. In addition to that, it would imply asymptotical stability, right? All right, so this is kind of annoying because it indicates stability, but especially for the cases where we know that the system is asymptotically stable, right? This is annoying. All right, moving on. Then the set of, and this is going to be really mathy, but let's try to understand one by one, right? Accumulation points of any trajectory. Okay, just try to change that, I guess, expression with then the set of termination points. Okay, this is, of course, whenever I talk something that's very close or distantly related to math, you need to take what I say with a really grain of salt, right? So I'm not a mathematician, right? I'm just a poor engineer. So okay, don't take it seriously, is what I'm saying. And then the set of and termination point of any trajectory. Okay, right? this is our initial point, and let's say, and this is another point, and they all converge to this limit cycle, let's say, right? So termination point of any trajectory. So in a way, you can consider this ellipsoid, right, geometric object being the termination of any trajectory, let's say, okay? All right, is contained in I. Okay, now we are going to explain what I is, the definition of I, where I is the union of complete trajectories, okay? But one more thing, contain entirely in the set. Okay, now you're like, hey, I'm a little confused. I don't know what is this all about. And all right, I am 100% with you. Okay, so you're not alone. And what this is saying is that then the set of, let me just try to make it clean. Then the set of all termination points, set of termination points of any trajectory is contained in I. Okay, what's I? I is the union of complete trajectories contained entirely in the set. Okay, what does it mean? We have this, right, and we have also some dynamics, okay, and I is this, I mean, we are going to look at the examples, but just write down the dynamics, okay, and then this set, in a way, express that, I mean, I'm seriously on the wrong waters, but just try to express that f of x, right, in that function. Right, or rather let's say this is S, right, like set S, okay? Just try to express the dynamics on that set, okay? And if you express that, and if you get like this, if you get like this, that would imply there will be a trajectory in that set. Okay, for example, I mean, we should talk about the tangible examples, I think, right? And the most prevalent example is a limit cycle. Okay, let's say we have some dynamical system, and let's say phi of x1 equals x1, x2 equals 0, right? And there is a limit cycle on, and the limit cycle is given by this, all right? And when you have that type of Lyapunov function, okay, and when you have that, right, when you have that, and then when you look at these cases, okay, meaning x1 dot plus x2 dot equals 0, right? And well, you will find by doing some manipulations, you will find, yeah, there is some limit cycle, okay, and the definition or the mathematical description of that limit cycle is this, right? Okay, So this limit cycle, all right, or rather this, right, this limit cycle is an example of complete trajectory contained entirely in this set. Okay, all right. So if we have an origin, and if we want to prove, yeah, this origin is asymptotically stable, we want no trajectory contained in that set, right? Okay, so what we are going to do is this. We are going to look at the description of v dot equals 0. We are going to look at the points that satisfy, that are in that set. Okay, and if on that point, when let's say this point, right, this point, and there is a, let's say there is a limit cycle, right, we will see that, well, this point first of all will be in that. Okay, and when we look at that point, or the motion of that point, we are going to see, yeah, it's 0, meaning it will stay on that, set, and this is the set, right? Okay, so but it's not a easy subject, right? Okay, so let's do that, delete. Okay, and delete this as well. Okay, so once again, then the set of termination points of any trajectory is contained in I, where I is the union of complete trajectories contained entirely in the set, right? Okay, let's say we have one equilibrium point and one limit cycle and two limit cycle, right? Limit cycle 2, number 2, let's say. And if we have that type of Lyapunov function, and if we look at that, or rather this is, if we look at this set, right, the points that are in that set, we are going to see that, let's say this is 0, and let's say this is phi 1 of x equals 0, and this is, let's say, phi 2 of x equals 0. We will see this will be, right, or we will be able to write that in 0, 0, right, union phi 1 of x equals 0, union phi 2 of x equals 0. Okay, right? This is such that sign. Okay, and then we will look at these points, okay, that are not the typical origin, right? Where we want to prove the stability of, and if we look at such points, and if we see x dot equals f of x, right, and computed on that set, if that is 0, right, we will see that, yeah, that is a limit cycle. All right, or the trajectories, rather complete trajectory contained entirely in the set. There is a or you know, if we have one trajectory, there will be like infinite trajectories, right? There is a complete trajectories contained entirely in this set. Okay, we will conclude that. All right. So, all right, and okay. Then the set of termination points of any trajectory is contained in I, where I is the union of complete trajectories contained entirely in the set. Okay, okay, and this is, we know, right? This is something that we are familiar with at this point, right? And this is continuing, right? The definition is not over. And if I contains no trajectory of the system except the except origin, let's say, except origin, right? Then the origin is asymptotically stable. Okay. Okay. Furthermore, yeah, this is like for the global case, right? If V is relatively unbounded, right? And this is the relative unboundedness, I guess, condition, right? Then the origin is globally asymptotically stable. Okay. And all right, let's continue. Let's continue. I will try to make it short, hopefully. Every time I say that, but yeah, all right. Things happen then. All right, this is the local version, right? So this is our Lyapunov function. Okay, and look at, this is not negative definite, but semi-definite, right? If for that Lyapunov function, hold only for x in some neighborhood D, right? Neighborhood of the origin where we want to prove the stability of, and the set, this is the set, right? Doesn't contain any trajectories of the system, and this is like, we are going to look at the set, right? And since this is local version, we are going to look at the set, and if we see that, yeah, that doesn't contain any trajectories of the system besides, of course, origin, right? Our point, then the local version of the invariance principle states that the origin is locally asymptotically stable. Okay. All right. Once again, I'm going to express that we have a dynamical system. Okay. We are going to write down our typical Lyapunov function. Okay. Then we are going to look at V dot. Okay. And then we are going to look at this set where V dot equals 0, right, on those points. Okay. And then we are going to look at the dynamics. We are going to look at the dynamics on that set, and if we see that, anyway, I'm not going to continue and with these abstract notations, right, notions, and if we see, then we will do some computations, and then we are going to look at that now. Say if x dot equals 0, meaning if we are on that point, we are on this point, and in addition to that, x dot is 0, meaning we stay on that point. If that happens, then we are going to say this given set, or the set, let's say the sets will include our origin. Okay. And then these two, right? And if we look at the dynamics for those points, and if we see that x dot equals 0, then we are going to say, yeah, there's something interesting going on with that set, and the chances are it may be a limit cycle or something, right? Or the kind of set of points where we want to look at, especially, right? Okay. All right. Again, this theorem is used for the cases where you have some asymptotically stable point, and you use typical Lyapunov function, and you look at the v dot, and you see it is not straightforwardly negative definite. Then you will use that. This is, I guess, the first time or first condition where you like to use that. And the second case you like to use that is you have some limit cycle, right? You have some limit cycle, and you have the geometric definition of that limit cycle, right? And you want to prove, I guess, prove the existence of limit cycle or something, right? This is not, by the way, again, take it with a grain of salt, everything I say. All right, let's continue. It's like, this is, the examples are I guess, the best way to learn about these subjects. First of all, I am going to state my opinion, right? I hate this type of equations, right? And why? Because I love this type of equations, and right, this is, I mean, there is an order to that. There is a beauty to that equation, right? X1, x2, right? And these are just the parameters, right? Okay. However, this looks, I mean, when somebody writes down that equation, I feel like they consider me as, or consider everybody as a mechanical engineer or something, right? Or maybe physicist, right? Okay, so I just want to say I don't like these type of equations. And if you don't like these type of equations, and if you are a control engineer, you are not alone. This is an emotional sport video at this point. All right, let's continue. Let's continue. Okay, this is the dynamics, and this is for pendulum, right? Okay, this is L, this is M, right? This theta angle, right? This is theta, okay, and mass and friction coefficient, okay, and gravitational acceleration, all right? And I guess this example is by the way, I'm using Slotin and Slotin's nonlinear control or nonlinear dynamical systems book, and also there are some Slotin lectures on the YouTube, right? Or maybe on MIT's website. But if you search, so maybe I should add the link down in the description, right? Slotin's MIT lectures, okay, and Slotin's book as well, nonlinear control book, right? Okay, and the Lassalle's invariant set theorem, and there's also something called invariant set principle or something, I don't know, anyway. And for that system, right, people just straightforwardly try to use total energy as a Lyapunov function, and they see that this Lyapunov function is not have the ability only to prove stability in the sense of Lyapunov, but not the asymptotic stability, right, where we like to have, right? And this was like confusing to them, and I guess this is the first, and every book, I guess, gives that example as the first use case of Lassalle's theorem. All right, okay, so because of that, I kind of study a little bit of physics for that. All right, so this is total energy. Let's try to use total energy as a Lyapunov function, right? Because we lack creativity, I guess. All right, and this is total energy and equals potential energy and kinetic energy, right? Okay, all right. Just go to your high school days, right? Where I hope you weren't bullied by that time. Okay, this is kinetic energy, and this is typical kinetic energy formula, right? Okay, so, and this is another v equals L times theta dot. This is another thing that you kind of need to know, right? And I didn't know that, by the way. Yeah, for full disclosure, right? And okay, this is what we have now. So let's expand this term. Okay, and let's theta equals x1 and theta dot equals x2. So this is P kinetic energy term. Okay, and let's look at the PE, potential energy term, and this is mgh, right? Go to your again high school days. And what is the h? Right, this was the confusing thing for me. Okay, let's consider that as height equals 0. Okay, all right, so let me get blue color. This is L, right? Okay, what is this? This is L times cos theta. Okay, so we will consider this as h. Okay, right. And so what is this? You know, the height from that quote unquote, this is ground, right? Or h equals 0 level. Okay, what is this? And this is, and since this is L, right? This is L minus L cos theta. Okay, right? All right, and we can just state that in 1 minus cos theta. Okay, so so h is this, m, g, and this is h. Okay, all right, that was a little bit of high school math. All right, so let's express theta as x1. All right, so let's sum them, right? Sum these two terms, and this is what we have. Somebody came up with this Lyapunov function, all right? So, and since we only want to have just v being positive, and this is, for example, we don't want to focus too much on these coefficients, right? So if v is a good Lyapunov function, so does m times v, or v over l square or something, right? But of course m and l square or r, right, they are just coefficients, they are just numbers, right? Okay, because the Lyapunov function is not unique, right? Okay, so maybe I could say, I could have said like v1 or v2, because I mean they are not equal, right? And this is the original, or this is the not the original, like this is the Lyapunov function that we are going to use, right? So we can just divide by l square, right? 1 and this, okay, and divide by m, okay, because we shouldn't, or we don't want to carry these terms, right? We want to, I guess, make the number of terms that are not totally relevant to our problem as much as small as possible. Okay, right, we want to keep them small, right? Okay, so just divide by m, right? Get rid of this m and get rid of this m. All right, at the end, this is our Lyapunov candidate at this point. Okay, let's analyze that. And it is in like the neighborhood around, right? Neighborhood around 0 origin. This is positive. We know that. So v being positive, so first constraint is satisfied. Okay, let's continue. So let's use that Lyapunov function. Okay, what's the second step? We need to use we need to compute v dot. Okay, this is v dot, right? So these are partial terms. Okay, again, explicitly I written that down, right? And when we do some manipulations, and when I say manipulations, I mean it's like there's no x1 term here, and this is just an right? Cos x1, and if we take the derivative of it, we get minus sine x1, right? Again, high school stuff. Again, take the derivative is cosine of x1, right? Okay. So, and there's minus over there. Okay. So at the end, if you do that high school math, you get that, and I don't know why I did that. This is like the expressions are like literally the same. All right. Anyway, stuff happens, right? So, and this is our dynamics, and we have x1 dot and x2 dot. So let's, by using this dynamics, let's substitute them, right? So x1 dot equals x2, x1 dot equals x2, and x2 dot equals this expression, and this is that expression. Okay, so just this term and this term, they cancel each other out, and this is what we have, and this is final form. Or okay, so yeah, okay, first we have a positive v, right? By the way, for we are looking at local stability. Okay, and the question is this term negative definite? And if you say yes, that will be a terrible rookie mistake. Okay, so don't be a noob, right? And if you have x1 and x2, okay, if you have two-dimensional system, you want to have x1 minus x1 square and minus x2 square as your v dot, or something like that, right? But if you only have that and not that, you will say this is negative semi-definite. Okay, all right, because x1 or rather x2 term is okay, but we don't have any information about x1, right, situation. So anyway, you want to see, let's say you have two-dimensional case system, right? You want to see something like that, right? Okay, and we only have this term, we don't have this term here. So this is not negative definite, but negative semi-definite, right? So v dot is this, but not this, right? Which is annoying because we want to prove asymptotic stability, and with this we are only able to prove stability in the sense of Lyapunov. Okay, but it's a pendulum, right? I mean, we know that it's this location will be asymptotically stable, right? All right, and due to this annoying technicality, right, we are not in a position to prove asymptotic stability directly, right? I mean, we are just using total energy, right? And I mean, by intuition says it should work, but it didn't work. So, and LaSalle is like a cool guy, and he says, all right, he says, when does this term become zero? I mean, when I say this term, I mean v dot term. All right, and LaSalle intervenes, right, at that point, and he asks, when does this term become zero? Okay, and okay, let's look at this term, and this is only zero when x2 is equals 0. Okay, all right, and he says, let's look at the dynamics for that case. Okay, this is an important point. Right? We have the dynamics, right? And this is our set. This set, okay. You will have your dynamics, and you also will have your set, right? Where v dot equals 0 on that, and you are going to, I mean, this is of course not a mathematical notation, right? But I mean, express your dynamics on that set. What do I mean by that? And this is important, right? And just write down your dynamics, okay, and then for example, it says x2 equals 0, right? Okay, x2 equals 0. Okay, just put 0 whenever you see on the right hand side. Whenever you see x2, swap it with 0. Okay, just this is 0 now, and this is 0 now. Okay, so all right, these are the, I guess you could say, projected dynamics. We projected our dynamical equation on that, I guess, virtual system, right? Virtual dynamics. So LaSalle says, okay, question again, when the dynamics, this is the new dynamics, right? Projected dynamics have the form, right? Meaning we have x equals f of x now, right? Maybe we can say L or something for LaSalle, right? When we have that, rather when, what is the case for f sub L of x equals 0? Okay, what is that case? The question, valid question, right? Okay, and okay, this is 0, but this is not 0, right? So we need to have that 0, but these are like the constants, right? So this is the condition. However, for, let's recall what sine of x is, right? But we are here, we are just looking at this point or neighborhood of that location. Okay, origin, this is origin, right? And of course there will be many zeros for that function, but for this area only this is the 0. Okay, meaning therefore the trajectories will converge to, right, first x2 goes to 0 because of that, because of v dot equals 0, and then x1 goes to 0 because we have looked at our projected dynamics, and this is the condition where it, I guess, I want to say the point doesn't move. Okay, all right, okay, so yeah, therefore the trajectories will converge to this point, but they will not stay in that set, this set, they will not stay in that set, right? Unless it's continuing, right? Unless f of x equals 0 for x in that set. And so this is a mathematical expression, right? Not for x, but for all x in whole state space, but for all x where the x points that are in that set, v dot equals 0 set. Okay, that satisfies this set condition. Okay, so let's continue. Okay, I know it was not a, I feel like, good example, and that's why I created my own example, right? Constructed my own example. Okay, so this is example 2, right? And I hope this will be clear, right? More clear. All right, so this is dynamical system, right? 2-dimensional. And question is this: is the origin an asymptotically stable equilibrium point of the system? Okay, this is the question. All right, so let us use the most typical quadratic Lyapunov function. Okay, this is the, I like to say, typical quadratic Lyapunov function. Okay, why? Because we can just write down v dot with that easily, right? This is an easy to keep that in mind. Okay, and so this is x1 dot, and this is x1 dot, and this is x2 dot, and this is x2 dot. Okay, let's substitute those terms. All right, so this is what we have, and let us arrange the terms. Okay, so the question is this negative definite function? And by just looking at that, but again, let me remind you, you want to see something like this for two-dimensional system. You would like to see some v dot similar to this, right? Okay, and is this similar to that? No, really not, right? Okay, the answer is not. But okay, let's come up with any other question. The question: when is this function 0? Okay, when I say this function mean v dot. Okay, all right. What are the points where v dot equals 0? Okay, so first of all, it has two terms, right? This is x1 times this larger expression. Okay, and this is x2 equals 0. When x2 equals 0, v dot equals 0. Okay, and also when this term equals 0, v dot also equals 0. Okay, this is union, right? Union. Okay, so this is the description of a geometric, I guess, object located on, right, or existing on state space. Okay, so let's put that x2, carry that to right hand side, right, and express it that way. Okay, so we have what I call S1 set and S2 set. This is S1 set and S2 set. So we need to look at S1 set or S1 case and S2 case. This is like my, I guess, terminology, right? All right, this is S1 case. Okay, let us look at S1 case, and the question is this: what is the form of the dynamics on that set? And it's like important, yeah. This is our dynamics, and this is our S1. Okay, when of course this is not a correct notation, right? Let me tell you about this, right? Okay. So what I am trying to say is that you have this dynamics and you want to look at the dynamics on those points. Okay, and what you will do is the following. This is x2 equals 0, right? Okay, whenever you see on the right hand side x2, just swap that with 0. Okay, because x2 equals 0, right? Okay, we want to look at the dynamics on that S1 set. Okay, all right, and this is it, right? So question: does the trajectory stay on S1? Well, no. By the way, what does it mean? Trajectory stay on. What does it mean, stay? Right? X dot equals 0 means it will not move. It means that, right? X dot equals 0 means it will not move, right? And does this term look like x dot equals 0 to you? And the answer is no, unless x1 equals 0. Yeah, x1 equals 0. For that case, yeah, this will be 0, right? And this expression will look like that, and the points will stay on that set. Okay, we will conclude that, right? Which would result in, right, this. And again, this is our origin. This is the point where we want to prove the stability of. Okay, yeah, which would result in origin point being asymptotically stable. Okay, there are two cases, S1 case and S2 case. We have looked at S1 case and there was no problem with that. And so let's look at S2 case. Okay, all right, let's continue. Okay, so what's S2 definition? S2 definition is that, okay, by the way, let me just, this is x1 and this is x2, right? Okay, let's say this is -1 and this, let's say this is +1 and this is 0, right? Let me look at this expression. Let's compute that for 2, right? 2 it will be like -8 plus 2 minus 6, meaning minus negative term. So let's say this is 1, this is -1, this is 0, because it's a polynomial, and like since it's third degree, right, there will be 3 zeros. Okay, so this is negative, right? It has that type of shape. All right. So we have these dynamics, and we want let me get another color. We want to look at the dynamics on that line, right? Okay, so what would you do? It says x2 equals this x1 term, right? X1 function. So whenever you see x2, here is x2 and here is x2, whenever you see x2, just substitute this term with x2. Okay, on the right hand side of the dynamics. Okay, all right, this is x2. Okay, we just substitute that, right? And here we just substitute that, right? Okay, so by arranging we get this. Okay, all right, again, question: does the trajectory stay on S2? What do we mean by that? We want to see x1 dot equals 0 and x2 dot equals 0. Okay, and the answer is no, unless x1 equals 0. Yeah, when x1 equals 0, yeah, this will be the case, which would result in origin point being asymptotically stable. Okay, however, I hear you saying, but sir, this, I mean, like, it is not like it has only 1 0, but it has 3 zeros. So why did you ignore that points? Because this is local case, and we are only looking at the neighborhood of that origin, right? Of course, if so, we are not able to prove global we are only able to prove local asymptotic stability, right, using Lassals. Okay, but that's a good thing, right? Okay, so I guess that's it. Let me just look at this. Yeah, okay, that's it. All right, so that's it. Again, thanks for watching, right? Don't forget to subscribe, and please look at this documentation with docx4 format, right, will be in GitHub page. You can just download that document, right, and from that GitHub link, and the link will be included in the description. Okay, and thanks.